In the late 19th century, the foundations of classical physics were well established, with scientists like Isaac Newton and James Clerk Maxwell providing the framework to understand the motion of objects and the behavior of light. Classical physics worked remarkably well for explaining phenomena on large scales, such as the motion of planets and the propagation of light through space. The laws of classical mechanics and electromagnetism were seen as comprehensive tools to describe most physical systems. However, these laws began to break down when scientists delved into the microscopic world, specifically the behavior of light and matter at atomic and subatomic scales. One of the key problems that scientists faced was the understanding of black body radiation. A black body is an idealized object that absorbs all radiation that strikes it and emits radiation at a specific temperature. The nature of this radiation had been a subject of growing concern in physics. Classical physics predicted that as the temperature of a black body increased, the intensity of radiation would also increase without bound at shorter wavelengths, a phenomenon that became known as the ultraviolet catastrophe. According to the classical laws of physics, this would lead to an infinite amount of energy being emitted in the ultraviolet range of the electromagnetic spectrum, which was clearly nonsensical. It was an outcome that contradicted both experimental observations and common sense, but no solution seemed apparent. The ultraviolet catastrophe was a direct consequence of the laws of classical mechanics and electromagnetism, and it revealed the inadequacy of these theories when applied to atomic and subatomic systems. This issue remained unresolved for years, until in 1900, a brilliant German physicist named Max Planck made a groundbreaking discovery that would forever change our understanding of physics and set the stage for the birth of quantum mechanics. Planck was working on the blackbody radiation problem when he proposed a radical new theory that challenged the very principles of classical physics. He suggested that the energy emitted by a black body was not continuous, as classical physics had assumed, but rather quantized, meaning it could only exist in discrete amounts. In other words, Planck theorized that the energy of oscillators within the black body could only take on certain specific values, and these values were related to the frequency of the radiation being emitted. This concept was completely new and revolutionary, as it went against the continuous nature of energy that had been assumed by classical physics. At the core of Planck's theory was the idea that energy could only be absorbed or emitted in specific, fixed amounts, or quanta. He introduced the concept of the quantum of energy, and he derived an equation that could explain the observed radiation spectrum of black bodies. This equation provided a way to accurately predict the intensity of radiation emitted at different wavelengths for a given temperature, and it matched experimental data perfectly. Planck's theory was a stunning success, as it resolved the ultraviolet catastrophe by showing that energy emission and absorption did not occur in continuous quantities, but instead in discrete packets. One of the key elements of Planck's theory was the introduction of a constant now known as Planck's constant, denoted by the symbol Ha. This constant played a central role in determining the energy of the quanta. The energy of each quantum, according to Planck's formula, was directly proportional to the frequency of the radiation. This relationship was expressed as E equals h nu, where E is the energy of a quantum, He is Planck's constant, and nu is the frequency of the radiation. This equation, though simple in form, had profound implications for the way scientists would understand energy and the nature of light in the future. Planck's constant became a fundamental constant of nature, a key parameter in the emerging field of quantum mechanics. The fact that energy could only be exchanged in fixed amounts, rather than continuously, was a major departure from classical thinking. It marked the first time that the very concept of energy was questioned, and it revealed a completely new and strange aspect of the physical world, a world where the smooth continuum of classical physics gave way to discrete units, a world where energy was not a fluid substance, but rather a collection of distinct packets. Before Planck's discovery, scientists had assumed that energy flowed smoothly and the laws governing the physical world were deterministic. If you knew the position and velocity of an object, you could predict its future motion with absolute certainty. The universe, in the classical view, was a predictable and mechanical machine, operating according to fixed laws. Planck's discovery, however, shattered this certainty. The idea that energy existed in discrete quanta, rather than flowing smoothly, suggested that the universe at small scales was governed by a different set of rules that were not deterministic but probabilistic. Although Planck's theory initially applied to black-body radiation, its implications stretched far beyond this specific problem. His idea that energy could be quantized was a concept that would resonate throughout the entire field of physics, paving the way for the development of quantum mechanics. The implications of this discovery were far-reaching, and the subsequent work of other physicists would build upon Planck's ideas to create a completely new framework for understanding the behavior of matter and energy at the microscopic scale. One of the first scientists to build on Planck's work was Albert Einstein. In 1905, Einstein used Planck's theory of quanta to explain the photoelectric effect, a phenomenon where light striking a metal surface could eject electrons from the metal. Classical wave theory could not explain this effect, as it predicted that the energy of the ejected electrons should depend on the intensity of the light, but experiments showed that only the frequency of the light mattered. Einstein proposed that light itself was quantized, and that the energy of light was carried by particles, now called photons. This insight, based on Planck's concept of energy quanta, was pivotal in establishing the particle-like nature of light and earned Einstein the Nobel Prize in Physics in 1921. Planck's work also laid the groundwork for the development of the Bohr model of the atom. Niels Bohr, building on Planck's ideas, introduced the idea that electrons in an atom could only occupy certain discrete energy levels. When an electron moved between these levels, it would emit or absorb energy in discrete amounts, a phenomenon that explained the observed spectral lines of hydrogen. This was another example of how Planck's theory influenced the development of quantum mechanics and revolutionized our understanding of atomic structure. In summary, Max Planck's discovery in 1900 marked the beginning of a new era in physics. His introduction of the concept of energy quanta and the associated Planck constant transformed our understanding of the physical world. Energy was no longer seen as a continuous quantity, but as a discrete entity that could only exist in fixed amounts. This groundbreaking insight resolved the ultraviolet catastrophe and led to the birth of quantum mechanics, a field of physics that would go on to reshape our understanding of matter, light, and the very nature of reality itself. Planck's work not only solved a long-standing problem in physics, but also opened the door to a new and strange world of microscopic behavior that continues to influence science and technology to this day. The ramifications of Max Planck's discovery went far beyond the resolution of the black-body radiation problem. It marked the beginning of a profound shift in the world of physics, one that would challenge long-held beliefs and force scientists to reconsider the very foundations of their understanding of the universe. Planck's insight into the discrete nature of energy created a ripple effect throughout the scientific community, prompting new lines of inquiry and leading to the development of quantum mechanics, a field that would forever change the way we look at the world around us. To fully appreciate the significance of Planck's work, it is important to understand the broader context in which it emerged. Before Planck, the prevailing view of the universe was largely governed by classical mechanics, as established by Isaac Newton. According to classical physics, physical systems were deterministic, meaning that the future behavior of a system could be predicted with certainty if its current state was known. This deterministic worldview was deeply ingrained in the scientific community, and any challenge to it was met with skepticism. Planck's quantization of energy, however, suggested that the universe at small scales was governed by a different set of rules, rules that were not deterministic but probabilistic. Energy, instead of being a continuous flow, was now understood to exist in discrete packets, or quanta. This was a revolutionary idea that directly contradicted the classical view of the world. Planck's discovery revealed that at the atomic and subatomic levels, nature did not follow the smooth, continuous paths that classical mechanics had assumed. Instead, energy interacted in discrete, quantized units. This realization was not easy for physicists to accept. It was a departure from the certainty and predictability of classical physics and introduced an element of randomness and uncertainty into the picture. The concept that energy could be quantized opened up a new set of questions about the nature of reality. If energy was not continuous, then what about other physical quantities? What were the underlying principles governing the behavior of matter at the atomic scale? These questions would form the basis for the new field of quantum mechanics. The probabilistic nature of the quantum world was highlighted further by the work of Niels Bohr, who extended Planck's ideas to the atomic model. In 1913, Bohr introduced a model of the atom in which electrons orbited the nucleus in discrete energy levels. Bohr proposed that these energy levels were quantized, meaning that electrons could only exist in certain specific orbits and could not exist in between. When an electron moved from one orbit to another, it would emit or absorb energy in the form of a photon, a particle of light. This was a direct consequence of Planck's theory of quantized energy. Bohr's model of the atom was a huge leap forward in understanding the structure of matter. It explained the discrete lines in the hydrogen atom's spectrum, a phenomenon that had puzzled scientists for years. The idea that energy levels were quantized and that light could only be emitted or absorbed in specific amounts was a direct extension of Planck's discovery. It showed that Planck's work had far-reaching implications, not only for the understanding of radiation, but also for the structure of atoms themselves. But it was not just the structure of atoms that was revolutionized by Planck's work. The entire field of quantum mechanics began to take shape in the years following his discovery. In 1925, Werner Heisenberg developed the matrix formulation of quantum mechanics, and in 1926, Erwin Schrödinger formulated the wave equation that described the behavior of particles as waves. These ideas were based on the assumption that the behavior of particles was not deterministic but probabilistic, a notion that was deeply influenced by Planck's quantization of energy. The introduction of the Planck constant, He, was also a pivotal moment in the development of quantum mechanics. Planck's constant became a fundamental quantity in the equations that described quantum systems. It was the bridge between the macroscopic world of classical physics and the microscopic world of quantum mechanics. Planck's constant provided a quantitative measure of the size of the quantum, the smallest possible unit of action in the universe. One of the most striking features of Planck's constant is its smallness. The value of Planck's constant, h approx 6.626 times 10 negative 34 joule seconds, is so small that it only becomes significant at very small scales, such as the scale of atoms and subatomic particles. In the macroscopic world that we experience in our everyday lives, the effects of quantum mechanics are not noticeable. However, at the atomic and subatomic levels, Planck's constant plays a crucial role in determining the behavior of particles and energy. The implications of Planck's discovery were not limited to theoretical physics, they also had practical consequences. The development of quantum mechanics led to the creation of technologies that have become central to modern life. The invention of the transistor, the laser, and the computer chip, all of which rely on principles of quantum mechanics, can trace their origins back to Planck's work. These technologies, which have revolutionized communication, computing, and entertainment, would not have been possible without the foundational concepts laid out by Planck and the physicists who followed him. One of the most significant outcomes of Planck's discovery was the birth of quantum field theory, which combines quantum mechanics with special relativity to describe the interactions between matter and energy. Quantum field theory has become the foundation for much of modern physics, including the Standard Model, which is the theory that describes the fundamental particles and forces of nature. The discovery of the Higgs boson in 2012, which confirmed the existence of the Higgs field, was a direct consequence of the framework developed by Planck and his successors. Planck's work also laid the groundwork for the development of quantum computing. Quantum computers, which rely on the principles of quantum mechanics, have the potential to revolutionize computing by solving problems that are currently intractable for classical computers. The concept of superposition, where a quantum particle can exist in multiple states simultaneously, and entanglement, where particles can be instantaneously connected across vast distances, are directly related to the principles first outlined by Planck. In conclusion, the discovery made by Max Planck in 1900 was not just a solution to a specific problem in blackbody radiation, but a pivotal moment that reshaped the entire field of physics. Planck's introduction of the concept of energy quanta and the Planck constant marked the beginning of quantum mechanics, a field that would revolutionize our understanding of matter, energy, and the universe itself. His work laid the foundation for many of the most important developments in modern science and technology, from the structure of atoms to the development of quantum computers. Planck's discovery was a key turning point in the history of physics, and its legacy continues to shape the world around us today. Max Planck's revolutionary insight into energy quanta transformed the understanding of physics and created the foundation for the field of quantum mechanics. This breakthrough came when Planck was grappling with the problem of black-body radiation, which was proving to be one of the most perplexing issues in theoretical physics. Classical physics, which had dominated the scientific world for centuries, simply could not explain the behavior of radiation at high frequencies, especially in the ultraviolet range. The classical theories predicted an unphysical result known as the ultraviolet catastrophe, which implied that an infinite amount of energy would be emitted by a hot object in the form of radiation. This prediction was clearly not in agreement with experimental observations, and it forced scientists to reconsider the validity of classical physics in certain contexts. At the time, the established theory of radiation, known as the Rayleigh-Jeans law, was based on classical mechanics and electromagnetism. According to this law, the energy emitted by a black body, an idealized object that absorbs all radiation and emits radiation at a characteristic temperature, should increase without bound at short wavelengths, especially in the ultraviolet range. However, experiments showed that this was not the case. Instead, the intensity of radiation peaked at a certain wavelength and then dropped off at both shorter and longer wavelengths. The failure of classical theory to explain this behavior was a major problem for physicists, and it was clear that something fundamental was missing from the current understanding of the physical world. It was in the face of this dilemma that Max Planck, a German theoretical physicist, proposed his groundbreaking theory in 1900. Planck suggested that energy could not be emitted or absorbed in a continuous flow, as classical physics had assumed. Instead, he proposed that energy was quantized, meaning it could only be transferred in discrete amounts, or quanta. This idea was revolutionary because it fundamentally challenged the classical assumption that energy could vary continuously and smoothly. Planck's hypothesis was based on the assumption that electromagnetic radiation could be emitted or absorbed only in specific, discrete units of energy, each of which was proportional to the frequency of the radiation. Planck's theory introduced the concept of a quantum of energy, which was a fixed amount of energy associated with each oscillating system in a black body. The energy of each quantum, Planck suggested, was directly proportional to the frequency of the radiation, and this relationship was described by the equation E equals h nu, where A is the energy of the quantum He is Planck's constant, and nu is the frequency of the radiation. This formula provided a way to calculate the energy of a quantum and offered a solution to the ultraviolet catastrophe, as it correctly predicted the observed radiation spectrum from black bodies. Planck's constant, h, became a key quantity in physics and is now one of the fundamental constants of nature. This radical departure from classical thinking had profound implications for our understanding of energy and matter. For the first time, the smooth, continuous nature of classical physics was replaced by a new framework in which energy existed in discrete packets. The idea of quantization opened up a host of new possibilities and led to the development of quantum mechanics, a theory that would eventually transform the way we understand the fundamental workings of the universe. But Planck's discovery did not just solve the problem of blackbody radiation, it also sparked a chain of events that would fundamentally alter the direction of physics and lead to some of the most profound discoveries of the 20th century. While Planck's theory provided a solution to the blackbody radiation problem, it also raised a host of new questions. One of the most important was the nature of the quantum itself. Planck had shown that energy could only be exchanged in discrete amounts, but the implications of this were far-reaching. If energy could only exist in fixed amounts, how did this affect the behavior of matter at small scales? Planck's work suggested that the behavior of particles at the atomic and subatomic levels was governed by entirely different rules than those that applied to macroscopic objects. This idea of quantization was a major departure from classical physics, which had always assumed that objects could exist in any state and that energy could flow freely and continuously. With Planck's work, the door was opened to a new and strange world in which particles and energy behaved in fundamentally different ways. Following Planck's discovery, several other physicists built on his work and developed the framework of quantum mechanics. Perhaps the most famous of these physicists was Albert Einstein. In 1905, Einstein used Planck's theory of energy quanta to explain the photoelectric effect, a phenomenon where light striking a metal surface causes electrons to be emitted. Classical wave theory could not explain this effect, as it predicted that the energy of the emitted electrons should depend on the intensity of the light, while experiments showed that it depended on the frequency of the light instead. Einstein proposed that light itself was quantized, and that the energy of light was carried by particles called photons. This idea, which was directly inspired by Planck's concept of energy quanta, won Einstein the Nobel Prize in Physics in 1921 and further established the quantum nature of light. Einstein's work on the photoelectric effect was a pivotal moment in the development of quantum theory. It not only provided strong evidence for the existence of energy quanta, but it also laid the groundwork for the idea that light, which had traditionally been viewed as a wave, could also exhibit particle-like behavior. This was a major breakthrough in understanding the dual nature of light, a concept that would later become known as wave-particle duality. The idea that light could exhibit both wave-like and particle-like properties was a key feature of quantum mechanics and challenged the classical view that waves and particles were distinct entities. In addition to Einstein, other physicists, including Niels Bohr, Werner Heisenberg, and Erwin Schrödinger, would go on to develop the theory of quantum mechanics, building on Planck's insights. Bohr, for example, used Planck's idea of quantized energy to develop a new model of the atom in 1913. According to Bohr's model, electrons in an atom could only occupy specific energy levels, and when they transitioned between these levels, they emitted or absorbed radiation in discrete amounts. This was a direct application of Planck's quantization of energy, and it provided a successful explanation of the spectral lines observed in hydrogen atoms. The development of quantum mechanics over the following decades would lead to a complete rethinking of the nature of reality. The principles of quantum theory showed that at the microscopic level, the behavior of particles was not deterministic, as classical physics had suggested, but probabilistic. This meant that, instead of being able to predict the exact position and momentum of a particle, scientists could only calculate the probability of finding a particle in a particular state. This probabilistic nature of quantum mechanics was formalized by Heisenberg's uncertainty principle, which stated that it was impossible to simultaneously know both the exact position and momentum of a particle. This idea was radically different from the deterministic worldview of classical mechanics and introduced a level of uncertainty into our understanding of the universe. In addition to its theoretical significance, Planck's work also had profound practical consequences. The ideas of quantum mechanics have led to the development of technologies that have transformed modern life. The invention of the transistor, the laser, and the computer chip are all products of quantum theory, and these technologies have revolutionized communication, computing, and entertainment. The field of quantum mechanics continues to be at the forefront of technological innovation, with new breakthroughs in quantum computing, quantum cryptography, and quantum teleportation, offering the potential to change the way we process information and communicate. In conclusion, Max Planck's discovery of the quantization of energy in 1900 was a watershed moment in the history of physics. His theory of energy quanta not only solved the long-standing problem of black-body radiation, but also laid the foundation for the development of quantum mechanics, a theory that has fundamentally changed our understanding of the universe. The implications of Planck's work were far-reaching, opening the door to a new world of probabilistic and discrete behavior at the atomic and subatomic levels. The legacy of Planck's discovery continues to shape the field of physics today, and his insights have led to some of the most important technological advancements of the 20th and 21st centuries. Planck's work is a testament to the power of human curiosity and the ability to rethink even the most basic assumptions about the physical world. The impact of Max Planck's discovery of energy quanta was profound, far beyond its initial resolution of the black-body radiation problem. His work became the cornerstone of a new era in physics, quantum mechanics, which would not only reshape how we understood the fundamental properties of matter and energy, but also revolutionize the technology that powers our modern world. The quantization of energy, which was central to Planck's theory, introduced the idea that energy levels were not continuous, but discrete, with each energy transition occurring in specific, fixed amounts. This insight was incredibly disruptive to the classical view of physics. For centuries, classical physics had governed scientific thought, built on the assumption that the physical world operated on deterministic principles. This worldview, most notably championed by Newtonian mechanics, held that if you knew the current state of a system, its position, velocity, and other measurable quantities, you could predict its future state with absolute certainty. But when it came to the atomic scale, classical physics faltered. It could not explain phenomena like black-body radiation, the photoelectric effect, or the discrete lines in atomic spectra. Planck's proposal that energy could be absorbed or emitted only in discrete packets, later known as quanta, was a radical departure from this deterministic view. Planck's hypothesis emerged from his work on black-body radiation, where classical physics had predicted an infinite amount of radiation at shorter wavelengths, an idea which clashed with real-world observations. To solve this problem, Planck introduced a constant, known today as Planck's constant, H, which governed the energy of these quanta. This allowed him to derive a new radiation formula, now known as Planck's law, that accurately described the observed spectrum of radiation emitted by a black body at any temperature. This was a groundbreaking achievement in itself, but its significance would extend far beyond the problem at hand. The key concept behind Planck's discovery was that energy is quantized, meaning that instead of being able to take any value, energy could only exist in specific, discrete amounts. This idea challenged centuries of thinking in physics, which had treated energy as a continuous substance. But Planck's theory didn't just solve the problem of black-body radiation, It opened the door to a new way of understanding the physical world at the atomic and subatomic scales. One of the major implications of Planck's theory was the shift from a deterministic worldview, where events could be precisely predicted, to a probabilistic one. The idea that energy could only exist in discrete packets meant that the universe, at least at microscopic scales, did not behave in the smooth, predictable manner that classical mechanics suggested. Instead, Planck's work introduced an element of uncertainty and randomness into the behavior of particles and energy. This shift in thinking would later be formalized by Werner Heisenberg with his uncertainty principle in 1927. Heisenberg's principle stated that it was impossible to know both the position and the momentum of a particle with absolute precision. This introduced a fundamental limit to our knowledge of the behavior of particles, something that could not be explained by classical physics. The uncertainty principle became one of the key features of quantum mechanics, a theory that replaced the predictability of classical mechanics with probabilities and wave functions. In the quantum world, particles existed in a range of possible states, with only the probability of their position or momentum being knowable at any given moment. The idea of energy quantization also had profound implications for the development of atomic theory. In 1913, Niels Bohr used Planck's quantization concept to explain the stability of the atom. Bohr proposed that electrons in an atom could only occupy specific energy levels and could not exist in between these levels. When electrons jumped from one energy level to another, they emitted or absorbed energy in discrete amounts exactly as Planck had predicted for blackbody radiation. Bohr's atomic model was one of the first major applications of Planck's ideas to atomic structure and provided an explanation for the discrete lines seen in the spectra of atoms, which classical physics could not explain. This development was foundational in the understanding of atomic structure and laid the groundwork for the development of quantum mechanics. But even more significant was the way in which Planck's ideas influenced the way scientists thought about the nature of reality. If energy existed in discrete packets, then it stood to reason that other physical quantities might also be quantized. The idea that the continuous nature of classical physics was just an approximation at larger scales, while the true behavior of the universe at the atomic scale was fundamentally discrete, was a fundamental shift in understanding. The implications of Planck's discovery were not limited to theoretical physics. The quantization of energy and the quantum mechanics that developed from it led to the invention of technologies that have become integral to modern life. The transistor, which is the backbone of modern electronics, relies on the principles of quantum mechanics to control the flow of electrical current. Similarly, lasers, which are now used in a wide range of applications, from telecommunications to medicine, are based on quantum principles, particularly the idea of stimulated emission, which was also grounded in Planck's work on energy quanta. The technological advances that stemmed from quantum mechanics have had a profound impact on society. The advent of quantum computing, which exploits the strange properties of particles at the quantum level, promises to revolutionize fields like cryptography, artificial intelligence, and data processing. Quantum cryptography, which leverages the principles of quantum mechanics to create unbreakable encryption, is already being used to secure sensitive information in fields like banking and national security. These advancements, all of which trace their origins back to Planck's discovery of quantized energy, demonstrate how far-reaching his ideas were in shaping the modern world. Even though Planck's work initially focused on the specific problem of blackbody radiation, it ultimately laid the foundation for much of modern physics. The discovery that energy is quantized was the first step in the development of quantum theory, which would go on to reshape not only our understanding of the microscopic world, but also the very nature of reality itself. The strange and often counterintuitive principles of quantum mechanics, such as wave-particle duality, superposition, and entanglement, are all based on the ideas Planck first introduced. The Planck constant, He, is now considered one of the most fundamental constants in physics, and its value has been refined over the years to an extraordinary degree of precision. It plays a critical role in the equations that describe the quantum world, from the behavior of particles to the interaction of light and matter. Planck's constant is so important that it is one of the 7 base units in the International System of Units, and its value is used as a standard for defining other units of measurement, such as the kilogram. Planck's discovery also marked the beginning of the end of the classical era of physics. The deterministic worldview that had dominated scientific thought for centuries began to crumble in the face of the strange and uncertain behavior revealed by quantum mechanics. The idea that the universe is not fully predictable, but instead operates according to probabilistic laws at the microscopic level, was a radical shift that still challenges our intuitions today. The field of quantum mechanics continued to evolve after Planck's time, with the work of physicists like Einstein, Bohr, Heisenberg, and Schrödinger, who extended Planck's ideas to form a complete theory of the microscopic world. The development of quantum mechanics led to the rise of the Standard Model, which is the theory that describes the fundamental particles and forces of nature, except for gravity. The Standard Model, built on the principles of quantum mechanics, has been incredibly successful in explaining the behavior of particles at the smallest scales, from the Higgs boson to neutrinos. Today, the legacy of Planck's work continues to shape the field of physics. Quantum mechanics is central to our understanding of the universe, and the principles of quantum theory continue to drive new discoveries and technological innovations. Max Planck's insight into the quantization of energy was not just a solution to a specific problem, it was the beginning of a new way of thinking about the universe. Planck's work laid the groundwork for the most successful theory of physics we have, and his legacy continues to inspire generations of scientists and engineers who are pushing the boundaries of what we know about the nature of reality itself. In conclusion, Max Planck's discovery of energy quanta in 1900 was not merely a scientific breakthrough, it was the start of a revolution in our understanding of the physical world. His theory of quantized energy opened the door to quantum mechanics, a field that would transform the way we see the universe and lead to some of the most important technological advancements of the 20th and 21st centuries. Planck's legacy is felt in everything from the devices we use every day to the fundamental theories that govern the cosmos, making his discovery one of the most significant turning points in the history of science. Max Planck's discovery of energy quantization and the development of quantum mechanics fundamentally transformed our understanding of the universe. His work set the stage for future discoveries and shifted the way scientists thought about matter, energy, and the laws of physics at the atomic and subatomic levels. Planck's ideas about energy quanta didn't just solve the problems surrounding black body radiation, they catalyzed an entire shift in the direction of modern physics, moving away from deterministic classical mechanics toward the probabilistic, uncertain world of quantum theory. Before Planck, classical physics, led by the works of Isaac Newton and James Clerk Maxwell, was well established as the framework for understanding the natural world. Classical mechanics offered precise, deterministic predictions about the motion of objects, and Maxwell's equations elegantly described electromagnetic radiation as a wave propagating through space in continuous patterns. Classical physics, based on these principles, was successful in explaining a wide range of physical phenomena, especially those involving macroscopic objects. However, when scientists turned their attention to phenomena occurring at the atomic and subatomic levels, they encountered problems that classical physics could not resolve. One such issue was the behavior of black-body radiation, a key problem in the understanding of thermal radiation. A black body is an idealized object that absorbs all radiation that hits it, emitting radiation at a characteristic temperature. Classical physics predicted that as the temperature of a black body increased, the intensity of emitted radiation would grow infinitely at shorter wavelengths, especially in the ultraviolet range. This prediction, known as the ultraviolet catastrophe, clearly contradicted experimental observations, where the intensity of radiation peaked at a certain wavelength and then decreased, especially at shorter wavelengths. This discrepancy between theory and experiment was one of the key problems that led Planck to develop his quantum theory. In 1900, Planck proposed a radical solution that energy was not emitted or absorbed in a continuous manner, as had been assumed by classical physics. Instead, he suggested that energy is quantized, meaning it is emitted or absorbed in discrete packets, or quanta. He postulated that the energy of oscillators within a black body could only take on specific values, which were related to the frequency of the radiation being emitted. This was a revolutionary insight because it fundamentally challenged the continuous nature of classical physics, introducing a discrete structure to energy itself. The formula that Planck derived to describe this quantized energy, E equals h nu, where A is the energy of a quantum, h is Planck's constant, and nu is the frequency of the radiation, successfully explained the observed radiation spectrum of black bodies and resolved the ultraviolet catastrophe. This was the birth of quantum theory. Planck's constant He, which was introduced in his formula, became one of the most important constants in modern physics. Its value is now considered a fundamental quantity in nature, helping define the scale of quantum effects. Planck's work on the quantization of energy didn't just solve a specific problem in black body radiation, it opened the door to a new realm of understanding in physics. One of the most profound shifts brought about by his work was the move away from the deterministic world of classical physics to the probabilistic nature of quantum mechanics. In classical mechanics, given the position and velocity of an object, you could predict its future with certainty. This deterministic framework worked well for objects at macroscopic scales, but at the atomic and subatomic levels, this predictability broke down. Planck's introduction of quantized energy suggested that, at the microscopic level, the laws of nature were not deterministic. Instead, the behavior of particles, atoms, and energy was inherently probabilistic. The outcome of an event at the quantum level could not be predicted with certainty. Instead, scientists could only calculate the probability of a given outcome, a concept that would become central to quantum mechanics. This departure from determinism was a revolutionary shift in thinking, and it paved the way for further developments in the field, especially through the works of Albert Einstein, Niels Bohr, Werner Heisenberg, and Erwin Schrödinger. Planck's work had a profound influence on the future of quantum mechanics, particularly in the development of the concept of wave-particle duality. One of the most famous applications of Planck's ideas was Albert Einstein's explanation of the photoelectric effect in 1905. Einstein extended Planck's theory of energy quanta to explain how light could behave as both a wave and a particle. He suggested that light, traditionally thought of as a continuous wave, also consisted of discrete packets of energy, which he called photons. This was a pivotal moment in the development of quantum theory, as it revealed that energy and light had a dual nature. Light could behave both as a wave, as described by Maxwell's equations, and as a particle, as described by Planck's quanta. Einstein's work on the photoelectric effect won him the Nobel Prize in Physics in 1921 and provided strong evidence for the validity of Planck's ideas. This marked the beginning of a new era in physics, one where particles and waves were no longer treated as separate entities, but rather as complementary aspects of the same underlying reality. The wave-particle duality, which described how both light and matter could exhibit both particle-like and wave-like behavior, became one of the cornerstones of quantum mechanics. It helped bridge the gap between the classical world and the quantum world, and it led to the development of the concept of quantum fields, which described the fundamental forces in particles in nature. Planck's ideas also led to major developments in the understanding of atomic structure. Niels Bohr, building on Planck's work, developed a model of the atom in 1913 that applied the idea of quantized energy levels to explain the behavior of electrons in atoms. According to Bohr, electrons in an atom could only occupy specific energy levels, and when an electron transitioned from one level to another, it would emit or absorb radiation in discrete amounts. Bohr's model successfully explained the discrete lines observed in the hydrogen spectrum and marked a significant advancement in atomic theory. Planck's quantization of energy was the basis for Bohr's model of the atom and was one of the first major applications of quantum theory to atomic structure. In the decades following Planck's discovery, quantum mechanics began to take shape as a full-fledged theory of the microscopic world. The development of the Schrödinger equation, Heisenberg's uncertainty principle, and the development of quantum field theory provided a comprehensive framework for understanding the behavior of particles at the atomic and subatomic levels. Quantum mechanics, as developed by scientists such as Schrödinger, Heisenberg, and Paul Dirac, revolutionized our understanding of the universe and led to the development of technologies that have transformed modern life. Perhaps one of the most profound impacts of Planck's work was its influence on technology. The principles of quantum mechanics have led to the creation of devices that are now essential to everyday life. The invention of the transistor in the 1940 seconds, for example, relied on quantum principles and revolutionized the world of electronics. Transistors made it possible to build smaller, faster, and more efficient electronic devices, leading to the development of everything from computers to smartphones. Similarly, the invention of the laser, which relies on the principle of stimulated emission of radiation, owes its origins to the work of Planck and his successors. Today, quantum mechanics continues to shape our understanding of the universe and our technological capabilities. Quantum computing, quantum cryptography, and other applications of quantum theory hold the promise of revolutionizing fields such as information processing, security, and communication. These technologies, which are still in the early stages of development, could change the way we process information and solve complex problems. In summary, Max Planck's discovery of the quantization of energy was a pivotal moment in the history of physics. His work not only solved the problem of black-body radiation, but also opened the door to the development of quantum mechanics, which has reshaped our understanding of the microscopic world. Planck's constant, the concept of energy quanta, and the probabilistic nature of the quantum world have all had profound implications for the way we understand matter and energy. Planck's work paved the way for the breakthroughs that would follow, from the development of atomic models to the invention of technologies that have transformed society. Today, the legacy of Planck's discovery continues to shape the field of physics and the technology that powers our world. The revolutionary nature of Max Planck's work did not stop at the initial solution to the black-body radiation problem. His introduction of the quantization of energy fundamentally transformed the entire landscape of physics, providing the cornerstone for the rise of quantum mechanics and influencing the development of numerous technological advancements that have become integral to modern life. However, the shift in thinking that Planck's discovery initiated was not easily accepted and would take decades to fully manifest in the broader scientific community. But once established, quantum mechanics would forever alter the way we understand the universe and our place in it. When Max Planck proposed his hypothesis that energy could only be emitted or absorbed in discrete packets, he was not immediately recognized as having struck upon a transformative new way of thinking. At the time, classical physics had been immensely successful in describing many aspects of the physical world, from the motions of celestial bodies to the properties of everyday matter. Classical theory, with its emphasis on continuous phenomena and predictable outcomes, was the bedrock of scientific understanding. The idea that energy might be quantized seemed bizarre, counterintuitive, and challenging to the entrenched notions of the time. Yet, despite initial resistance, Planck's theory quickly proved to be a game-changer. The equation E equals hn nu, where E is the energy of a quantum, h is Planck's constant, and nu is the frequency of radiation, provided the first accurate description of blackbody radiation. His formula predicted that the energy radiated by a perfect black body, a theoretical object that absorbs all incident radiation, depended not on the intensity, as classical theory would have suggested, but rather on the frequency of the radiation being emitted. This insight allowed Planck to resolve the ultraviolet catastrophe, a paradox that had plagued scientists for years. The success of Planck's formula, which matched experimental observations, made it clear that something fundamental about energy and its interactions with matter had been misunderstood in classical physics. What made Planck's contribution so revolutionary was that it shifted the paradigm from the continuous flow of energy to a discrete model, one in which energy existed in packets, each corresponding to a particular frequency. This insight laid the groundwork for the development of quantum mechanics, a theory that would completely reframe our understanding of particles, light, and the universe itself. The quantization of energy meant that rather than flowing smoothly, as classical theory suggested, energy could only exist in small, indivisible quantities. This idea led to the development of a new framework for understanding atomic and subatomic processes, which would challenge the predictability and certainty of classical physics. Planck's quantization of energy did not just influence theoretical physics, it also forced a re-evaluation of the nature of reality itself. In the world of classical physics, objects behaved deterministically, meaning that the future behavior of a system could be predicted with complete certainty if its current state was known. In contrast, quantum mechanics introduced the concept of probability, not certainty. The behavior of particles in the quantum world could only be described in terms of probabilities, and not in terms of specific, deterministic outcomes. This shift from a deterministic to a probabilistic view of the world was one of the most profound consequences of Planck's work. The probabilistic nature of quantum mechanics was later formalized by Heisenberg's uncertainty principle, which states that it is impossible to simultaneously know both the position and momentum of a particle with perfect precision. This inherent uncertainty was a direct consequence of Planck's discovery that energy is quantized. The mathematical frameworks that followed Planck's insight suggested that, at microscopic scales, uncertainty and probability were fundamental features of nature, rather than merely imperfections of measurement. For physicists, this was a challenging concept to accept, but it marked the beginning of a new era in physics, where probability and wave functions replaced the deterministic Newtonian view of the universe. Planck's work directly influenced subsequent developments in the understanding of atomic and subatomic structures. Niels Bohr, for example, took Planck's idea of quantization and applied it to the behavior of electrons in atoms. In 1913, Bohr proposed a model of the atom in which electrons could only occupy discrete energy levels. Electrons in an atom, according to Bohr's model, could not exist in intermediate states, but could only transition between specific energy levels. When an electron jumped from one level to another, it emitted or absorbed radiation corresponding to the difference in energy between those levels. Bohr's model of the atom was based on the same principles of quantization that Planck had introduced, and it successfully explained the spectral lines observed in hydrogen. The development of Bohr's model was one of the earliest applications of quantum mechanics to atomic theory, and it marked a shift from the classical view of atoms as small, indivisible spheres to a model in which the atom was composed of discrete energy levels and probabilistic behavior. Einstein's work on the photoelectric effect, which earned him the Nobel Prize in 1921, further built on Planck's ideas. Einstein applied Planck's concept of quantized energy to explain how light could cause the emission of electrons from a metal surface. Classical wave theory could not explain the photoelectric effect, as it predicted that the energy of emitted electrons should depend on the intensity of light. However, experiments showed that the energy of the emitted electrons depended on the frequency of the light, not its intensity. Einstein proposed that light consisted of discrete packets of energy, or photons, and that these photons were responsible for the emission of electrons. Einstein's explanation of the photoelectric effect provided further evidence for Planck's quantization of energy and was a pivotal moment in the development of quantum theory. The ideas that emerged from Planck's discovery of energy quantization formed the bedrock of quantum mechanics, and they had profound implications for the understanding of the microscopic world. The work of physicists like Bohr, Einstein, Heisenberg, and Schrödinger continued to build on Planck's insights, culminating in the development of a full quantum mechanical framework to describe the behavior of atoms and subatomic particles. Quantum mechanics introduced the concept of wave-particle duality, where particles like light and electrons could exhibit both wave-like and particle-like behavior depending on the circumstances. This duality was a direct consequence of the quantization of energy, as particles in the quantum world could no longer be described as simply localized objects or traveling waves. Instead, they existed in a superposition of both states, with their behavior determined by the probabilities of these states. As quantum mechanics developed, it became clear that this new framework had profound implications not only for theoretical physics, but also for technology. Many of the technologies that shape our modern world, from semiconductors and transistors to lasers and medical imaging devices, are based on the principles of quantum mechanics. The understanding that energy levels are quantized and that particles exhibit probabilistic behavior allowed for the development of technologies that would have been inconceivable under the classical framework. The transistor, which forms the backbone of modern electronics, is one such example of a technology rooted in quantum mechanics. Similarly, lasers, which rely on the stimulated emission of photons, are based on the quantum principles first introduced by Planck. One of the most exciting areas of modern research, based on Planck's discovery, is quantum computing. Quantum computers rely on the principles of superposition and entanglement, which are fundamental aspects of quantum mechanics, to perform computations in ways that classical computers cannot. Quantum computers have the potential to solve problems that would be intractable for classical computers, including problems in cryptography, optimization, and simulation. These advancements, which trace their origins back to Planck's quantization of energy, could revolutionize the field of computing in the coming decades. In conclusion, Max Planck's discovery of the quantization of energy in 1900 was a pivotal moment in the history of physics, setting in motion the development of quantum mechanics and fundamentally changing our understanding of the universe. Planck's work not only solved the problem of blackbody radiation but also introduced the idea of discrete energy levels, which would lead to a complete rethinking of the nature of matter and energy. His ideas laid the foundation for future breakthroughs, including the development of atomic models, wave-particle duality, and quantum computing. Planck's legacy continues to shape modern physics and technology, and his contribution to science will remain one of the most important turning points in the history of human understanding. Max Planck's work on the quantization of energy in 1900 fundamentally shifted the way physicists understood the behavior of energy and light. One of the most profound implications of his theory was the move away from classical physics, which had assumed energy could be emitted and absorbed continuously, toward a quantum world where energy exists in discrete packets, or quanta. This new paradigm became the cornerstone of quantum mechanics, reshaping the course of physics forever. Planck's introduction of the concept of the quantization of energy came from his attempt to solve the blackbody radiation problem. Classical physics had predicted that, as the temperature of a black body increased, the intensity of radiation it emitted would continue to increase indefinitely at shorter wavelengths, a phenomenon known as the ultraviolet catastrophe. However, experimental results showed that radiation intensity did not continue to rise at short wavelengths, but instead peaked and then declined. To resolve this discrepancy, Planck proposed that energy could only be emitted or absorbed in discrete quantities proportional to the frequency of radiation, a concept that would eventually become known as energy quanta. Planck's equation, E equals h nu, where E is the energy of a quantum, he is Planck's constant, and nu is the frequency of radiation, provided the first accurate model for blackbody radiation. This idea of energy quantization not only solved the problem of blackbody radiation, but also introduced a revolutionary concept in physics. Energy was no longer a continuous variable, but existed in fixed units. This was a fundamental departure from the classical view of the world, which had assumed that energy could vary smoothly, without restriction. By introducing the Planck constant, he, a fundamental constant of nature, Planck provided a tool to quantify these discrete energy levels, laying the groundwork for the development of quantum mechanics. The consequences of Planck's discovery reached far beyond the blackbody radiation problem. It marked the beginning of a shift from classical determinism to quantum probabilism. Classical physics, as established by Newton and Maxwell, was deterministic. If you knew the initial conditions of a system, you could predict its future behavior with certainty. In contrast, Planck's work, alongside later developments in quantum mechanics, suggested that at the atomic and subatomic levels, the behavior of particles was inherently uncertain and could only be described probabilistically. This shift was formalized by Heisenberg's uncertainty principle, which stated that one cannot simultaneously know the exact position and momentum of a particle. This uncertainty at the quantum level marked the end of the classical worldview and introduced a new, fundamentally probabilistic approach to understanding nature. Furthermore, Planck's idea of quantization provided the basis for understanding atomic structure. Niels Bohr used Planck's quantization of energy to propose his model of the atom in 1913. Bohr's model suggested that electrons in an atom could only occupy discrete energy levels, and when they moved between these levels, they emitted or absorbed radiation in the form of specific, quantized amounts of energy. This explained the discrete spectral lines observed in hydrogen and marked a major step in the development of quantum mechanics. Bohr's work would be built upon by other physicists, such as Schrödinger and Heisenberg, who developed the broader framework of quantum theory. The impact of Planck's work is still felt today. His ideas about quantization laid the foundation for many of the technologies we rely on, such as transistors, lasers, and the development of quantum computing. Quantum mechanics, which traces its origins to Planck's work, continues to revolutionize science and technology, from advances in computing to breakthroughs in cryptography and communication. Planck's theory of energy quanta, though initially a theoretical solution to a specific problem, opened the door to an entirely new way of understanding the universe, one that continues to shape our world in profound ways. Max Planck's discovery that energy is quantized fundamentally changed the trajectory of physics. Before his work, scientists viewed energy as a continuous flow, with classical physics explaining phenomena through smooth transitions. However, Planck's theory of energy quanta introduced the idea that energy exists in discrete packets, fundamentally altering the course of scientific thought. This change led to the birth of quantum mechanics, which would go on to redefine our understanding of the microscopic world. Planck's work began with his attempt to explain blackbody radiation. Classical physics had failed to describe the radiation emitted by a perfect black body, a material that absorbs all incoming radiation and emits radiation based on its temperature. The ultraviolet catastrophe, a paradox where classical theory predicted an infinite amount of radiation in the ultraviolet spectrum, exposed the inadequacy of classical theories. Planck's breakthrough was his realization that energy could not be emitted or absorbed continuously, as classical theory suggested. Instead, he proposed that energy is quantized, existing in discrete amounts. His equation, E equals h, nu, where E is energy, A is Planck's constant, and nu is frequency, explained the observed radiation curve, effectively resolving the ultraviolet catastrophe. The significance of Planck's discovery extended beyond black body radiation. It introduced the idea that energy at the atomic level behaves differently than at macroscopic scales. Planck's theory suggested that energy transfers occur in fixed quantities, or quanta, rather than in a continuous stream. This was a profound shift from classical physics, where energy was assumed to flow smoothly and predictably. By quantizing energy, Planck opened the door for a new way of thinking, where particles and energy could only exist in specific, fixed states. The concept of energy quantization had deep implications for the study of atoms. Planck's ideas directly influenced Niels Bohr's development of his atomic model in 1913. Bohr applied Planck's notion of quantized energy to the structure of the atom, suggesting that electrons orbiting the nucleus could only occupy specific energy levels. Electrons moving between these levels would emit or absorb energy in discrete amounts, explaining the spectral lines observed in hydrogen. This marked a major step in the understanding of atomic structure, directly building on Planck's early work. Moreover, Planck's discovery marked the transition from a deterministic view of the universe, where outcomes could be predicted precisely, to a probabilistic framework. Classical physics assumed that if the initial conditions of a system were known, future behavior could be precisely predicted. However, Planck's theory, combined with the work of later physicists like Heisenberg and Schrödinger, demonstrated that, at the quantum level, events occur with inherent uncertainty. This shift in thinking led to the development of quantum mechanics, where particles and energy are described by probabilities rather than certainties. The impact of Planck's work extends beyond theoretical physics into the development of modern technologies. Quantum mechanics, based on Planck's ideas, underpins many technologies, including semiconductors, lasers, and MRI machines. The principles of quantum mechanics, from energy quantization to wave-particle duality, are fundamental in the design of modern electronics and medical technology. The continued exploration of quantum mechanics promises future innovations, such as quantum computing, which could revolutionize industries like cryptography, artificial intelligence, and data processing. Planck's discovery of energy quanta has not only reshaped our theoretical understanding of the universe, but also paved the way for technological advancements that have had a profound impact on everyday life. In summary, Max Planck's discovery of quantized energy was a pivotal moment in the history of science. His introduction of the concept of energy quanta resolved long-standing issues in the understanding of radiation and laid the foundation for quantum mechanics. His theory challenged classical physics, introducing a new, probabilistic framework for understanding the atomic and subatomic worlds. Planck's work has had far-reaching consequences, influencing the development of atomic theory and quantum mechanics, while also driving technological advancements that continue to shape modern society. Max Planck's introduction of energy quantization marked the beginning of a new era in physics. Before his groundbreaking work, classical physics governed our understanding of the physical world, providing explanations for phenomena that worked well at macroscopic scales. However, when physicists turned their attention to the behavior of matter and energy at atomic and subatomic scales, classical theory was unable to explain certain behaviors, especially in the case of radiation. Planck's discovery not only resolved one of these key issues, but also initiated the shift from classical to quantum physics. Planck's most significant contribution came through his solution to the black body radiation problem. Blackbody radiation refers to the radiation emitted by a perfect black body, an idealized object that absorbs all radiation that strikes it and emits radiation based on its temperature. Classical physics, specifically the Rayleigh-Jeans law, predicted that the intensity of radiation emitted by a blackbody would increase indefinitely at shorter wavelengths, leading to the ultraviolet catastrophe. However, experimental data contradicted this prediction, showing that the intensity of radiation increased at longer wavelengths and then decreased. Planck's insight was that energy could not be emitted or absorbed in a continuous flow, as classical physics assumed. Instead, it was quantized, existing in discrete units. This idea helped explain the observed radiation spectrum and resolve the ultraviolet catastrophe. The introduction of quantized energy by Planck led to the realization that energy is not a continuous variable, but exists in discrete packets, each corresponding to specific frequencies. This was the birth of the concept of quanta, and Planck's constant, denoted as h, became a fundamental quantity in physics. Planck's equation E equals h dot nu, where E is the energy of a quantum, h is Planck's constant, and nu is the frequency, provided a mathematical relationship that accurately described the emission of radiation by black bodies. The quantization of energy was a revolutionary departure from the continuous nature assumed by classical mechanics. Planck's theory also marked the beginning of the shift from a deterministic worldview to a probabilistic one. Classical physics, particularly Newtonian mechanics, was based on the principle of determinism. If the current state of a system was known, its future state could be predicted with certainty. However, the discovery that energy is quantized suggested that events at the atomic and subatomic levels could not be predicted with absolute certainty. Instead, they were governed by probabilities. This departure from determinism would be further developed by later quantum theorists, including Werner Heisenberg, who formalized the uncertainty principle, and Niels Bohr, who applied Planck's quantization ideas to atomic structure. The development of Planck's ideas influenced the next generation of physicists, particularly Niels Bohr, who used quantization to explain atomic structure. Bohr's atomic model, developed in 1913, posited that electrons in an atom could only occupy specific energy levels, and the energy associated with these levels was quantized. When electrons transitioned between these levels, they emitted or absorbed radiation in discrete amounts, corresponding to the energy difference between the levels. This model explained the discrete spectral lines observed in hydrogen and was the first step toward a quantum description of atomic systems. One of the most profound aspects of Planck's work was its ability to bridge the gap between classical and quantum physics. Classical physics, with its deterministic equations, worked well for larger-scale phenomena, but failed to explain the behavior of atoms and molecules. Planck's theory, however, introduced a new framework that allowed for the description of atomic and subatomic systems, where quantum effects became significant. This framework not only explained radiation behavior but also laid the groundwork for the development of quantum mechanics, which would evolve into a comprehensive theory to describe the microscopic world. The impact of Planck's work extended beyond theoretical physics to technological advancements. Quantum mechanics, born from his theory of energy quantization, has been the foundation for numerous innovations, including semiconductors, lasers, and modern computing. The invention of the transistor in the 1940 seconds, based on quantum mechanics, revolutionized electronics and laid the foundation for the digital age. Similarly, lasers, which rely on the principles of stimulated emission, have transformed industries ranging from telecommunications to medicine. The continuing exploration of quantum principles holds the promise of future breakthroughs in fields such as quantum computing, which could revolutionize computing power by exploiting quantum states to solve problems that are currently beyond the reach of classical computers. In conclusion, Max Planck's introduction of energy quantization was a pivotal moment in the history of physics. His insights not only solved a critical problem in black-body radiation, but also introduced the concept of discrete energy levels, which would later form the foundation of quantum mechanics. His work marked the transition from the deterministic world of classical physics to the probabilistic world of quantum theory, shaping the future of atomic and subatomic physics. Beyond its theoretical implications, Planck's discovery has had far-reaching consequences in technology, driving innovations that continue to impact society today. Planck's legacy is not just in his equations or theories, but in the revolutionary shift he initiated, fundamentally altering our understanding of the universe. Max Planck's discovery of energy quantization in 1900 was a pivotal moment in the history of physics, initiating the birth of quantum mechanics and radically altering our understanding of the universe. Planck's work came in the context of the black-body radiation problem, which classical physics could not solve. Classical physics, particularly the Rayleigh-Jeans law, predicted that radiation intensity would increase indefinitely at shorter wavelengths, leading to the ultraviolet catastrophe, a paradox that contradicted experimental observations. Planck's solution to this problem was the introduction of energy quanta, a concept that energy is emitted or absorbed in discrete, fixed amounts rather than continuously. Planck's introduction of the quantum of energy was revolutionary. By suggesting that energy could only exist in specific quantities, Planck defied centuries of classical thinking, which had viewed energy as a continuous variable. His equation, E equals h nu, where E is the energy of the quantum, He is Planck's constant, and nu is the frequency of the radiation, described the relationship between energy and radiation frequency. This formula resolved the ultraviolet catastrophe, providing an accurate description of black-body radiation and laying the groundwork for the entire field of quantum theory. The concept of quantized energy shifted the paradigm from classical physics to quantum mechanics. The implications of Planck's theory went beyond solving a single problem in radiation. It marked the beginning of a shift in the fundamental understanding of physics. Before Planck, the universe was seen through the lens of classical physics, where phenomena were considered to be continuous and deterministic. Planck's introduction of quantization suggested that the universe, at the atomic level, behaved in a discrete manner. This insight would become a cornerstone of quantum mechanics, where particles and energy levels were governed by probabilities rather than certainties. The deterministic worldview of classical mechanics gave way to the probabilistic nature of quantum theory. Planck's constant h became a key quantity in understanding the microscopic world. The constant defines the scale of quantum effects, being central to the equations that describe phenomena at atomic and subatomic levels. Its small value is critical because it only becomes noticeable at extremely small scales, such as those of individual particles in atoms. This constant is now one of the fundamental constants of nature, providing the bridge between classical and quantum physics. Planck's constant is integral not only in theoretical physics, but also in practical technologies like semiconductors and lasers. Planck's discovery also influenced the development of the Bohr model of the atom. In 1913, Niels Bohr applied Planck's concept of quantized energy to the atom, proposing that electrons in atoms occupy specific, quantized energy levels. Electrons could not exist in between these levels, and when they transitioned from one level to another, they emitted or absorbed radiation corresponding to the energy difference between the levels. This was the first successful explanation of the discrete spectral lines observed in hydrogen and was a direct application of Planck's ideas, marking a significant step in the development of atomic theory. Planck's work also fundamentally altered the philosophical understanding of reality. Classical physics was deterministic, meaning if the state of a system was known, its future could be predicted with certainty. Planck's introduction of quantization along with subsequent developments in quantum mechanics, such as Heisenberg's uncertainty principle, shifted this deterministic view to a probabilistic one. The inherent uncertainty in predicting the behavior of particles at the quantum level meant that science could no longer rely on the certainty of classical physics, but must account for probabilities and uncertainties at the atomic scale. The far-reaching consequences of Planck's work are most evident in the technological advancements that arose from quantum mechanics. Technologies such as semiconductors, which form the basis of modern electronics, and lasers, which have applications in communications, medicine, and industry, owe their existence to the principles of quantum mechanics. Additionally, Planck's work laid the foundation for quantum computing, a field that promises to revolutionize information technology by solving problems that are currently beyond the reach of classical computers. In conclusion, Max Planck's discovery of energy quantization was more than just a solution to the blackbody radiation problem. It was the catalyst for a transformation in the way we understand the physical world. His introduction of energy quanta, the development of Planck's constant, and the shift from a deterministic to a probabilistic view of the universe marked the birth of quantum mechanics. His work reshaped not only theoretical physics but also gave rise to a new generation of technologies that continue to shape modern society. The legacy of Planck's discovery is profound, and its influence persists, powering advancements in science and technology to this day.